All right, so I think now we can start. So for this week's string theory seminar, very happy to have Masamichi Miyaji from Riken Items in Tokyo, and he will tell us about the perturbative Hilbert space of closed universes in JT gravity. Please, thank you.
Thanks for the introduction. I'm to talk, and I'm very happy to be coming back to Berkeley. I used to be a postdoc at here from 2019 to 2022. So today I'm going to talk about this recent topic about closed universe. So in today's talk, I'll be talking about the perturbative Hilbert space of the closed JT. So this is work in progress with post Sumio Sek. He's a postdoc at UC Santa Cruz. And Kotaro Shimio is a PhD student at Riken. So let me begin by the motivation. So we know that so in ADS-JT, we know very well about how to consider Hilbert space because we have a gravity dual. We have a dual CFT, which has a precise CFT, precise Hilbert space. But on the other hand, when we go into the closed universe or Dosita space, this question becomes very non-trivial because there's no such duality like ADS-JT. And there are some approaches like ADS-JT, but it is the status is not yet accurate. So to attack this problem of constructing the Hilbert space of closed universe, probably the most simplest and still non-trivial theory of gravity would be the JT gravity, which is the two-dimensional gravity with the atomic. And in particular, the DS-JT path integral with the Dirichlet boundary condition can be continued from ADS functional functions, such as the global ADS can be obtained from ADS disk, and also the bound Dosita space can be obtained from ADS double. So we know how to do path integral, at least perturbative, on Dosita space. So we are optimistic about the construction of Hilbert space in this theory. And so recent, very interesting discussion about the non-perturbative Hilbert space closed universe suggests a very striking prediction. So how it goes is follows. So you consider a finite n theory. So you use basically the duality between JT gravity to the boundary 0% dimensional mathematics theory. So you can basically talk about the finite n version of JT gravity using the mathematics. And the interesting argument was that using replica trick based on the Euclidean one-hole calculation, the Hilbert space of non-perturbative closed universe was argued during last session. So the belief argument is as follows. So suppose you consider the over-concrete basis of your closed universe Hilbert space. So the A is the over-concrete basis, and you consider the maximum rank of operator. So this operator rho. So the rank of this operator should correspond to the dimensions of your Hilbert space. And to compute the rank, it's always convenient to consider replicative. So you take the trace rho to the n, and which is correspond to the path integral, the gravitational path integral with the boundary condition, A1, A2, A2 to AN, and you rest this space-time, fractional space-time with Euclidean optics. But from this figure, you can see that if you just rotate these indices, this is simply equal to the trace to the n. So this argument suggests that the ground code rho is 1, and therefore the Hilbert dimension is 1. So this is kind of striking, and it seems like there's no way to express the richness of a universe, but there's interesting proposal like including the observer or considering a subsystem that's can explain the richness of spark dimension physics. So yeah, but this is for the non-particle aspect. And before going into the non-particle one, I think it's very nice to clarify what's the Hilbert space structure for the particle one. So that is one of the main themes of my talk. So it is very common to integrate the partition function with the leadership boundary condition as the inner product or a matrix set. So for example, so you consider the Rosetta partition function, then it corresponds to the wave function of Hartree state on the length and the atom basis. And the bounds Rosetta space as a matrix element of two lengths and the atom state. So such correspondence of boundary condition is states as is indeed precise in non-gravitative QFTs. But however, once in the case of gravity, there's a non-trivial constant is happening, so the story changed to somehow. So that's one important aspect of gravity. So in gravity, so so that's the extension. So anyway, so in the case of gravity, there's the Hamiltonian momentum constraint that makes you get different time cycle equivalent and so on. So in short, these L5 states are overcompleteness. They are not orthogonal to each other, and they are linearly dependent. So let me explain the main difference from usual QFT with gravity, in particular in closed groups. So since the gravity is the gauge theory, so it has a different morphism variance. And in closed universe, there's basically different time sizes are gauge equivalent to each other. So they are these two states in the same space-time they are equivalent. So this Hamiltonian constraint imposes or breaks some usual property of the QFT, such as factorization. So this failure of factorization is also explained in the paper on canonical quantization. where he pointed out that the resolution of identity this cannot be constructed just by summing over intermediate boundary conditions. So you have to do some work to construct the resolution of identity. So these are the figures that explain this. So let me just consider the global consider space with this time size being fixed at a constant extreme curvature space. So if you want to construct the resolution identity by just setting the intermediate state as the constant extreme curvature state, it is obvious that it's over-complete because you can consider this time size that has a constant extreme curvature it's far from me. There's many time sizes that have a constant extreme curvature. So if you just insert the resolution of identity by just summing over all the constant extreme curvature states, then such decomposition give you it gives you the infinity many times of the original gravitation bound. It's giving you the infinity many times the same state. So A is just the length density of your answer. So you have the total density divided by A. And K is here A times extreme curvature. Yeah, so basically, so the problem is that, so the problem or the feature you need to be careful about is that your conditional time size, so the time size may not be. And if you want to, so therefore, in particular, if you consider the matrix element, the decomposition in terms of this AK state doesn't factorize. But this can be this problem can be resolved if you consider at least locally unique time size, such as the geodesic time size, where city captures them. So given that such a overcounting problem, so we now consider how to construct the Hilbert space or the closed universe, or in general the gravity. So what is nice about the BRST construction formalism is that this BRST homology has a rich enough structure that can accommodate Hilbert space or the closed universe. So in BRST formalism, one basically consider the gauge-fixed action, so that the theory has the nilpotent BRST symmetry, which is global symmetry, and basically diffeomorphism symmetry becomes the BRST transformation. And the gauge parameter becomes the ghost field, and the momentum of the ghost has a BRST transformation given by the Hamiltonian momentum constant. So the nilpotency of the BRST transformation allows you to construct a cohomology, basically the kernel of the BRT charge, the BRT operator divided by image of BRT. So this cohomology can be used to construct the Hilbert space. So we have the so-called global ghost symmetry. So it has a global U1 symmetry, and with charge assigned to the ghost speed as the 1, and for the momentum being the ghost number -1. And BRC transformation itself has a charge 1. And for each sector in the ghost number, we have a candidate Hilbert space that can be used to express the Hilbert space for first numbers. So at ghost number 1, -1, let's consider the states annihilated by all the ghost momenta. So in this space, the cohomology is given by states that are annihilated by all the Hamiltonian momentum. So this is what we often consider as the states that satisfy the real unification. But we can also consider other type of states by looking at the different ghost number set. So at ghost number 0, let's consider the states annihilated by the, so I indices is the spatial indices, and 0 is the time indices. So we can consider state annihilated by ghost momenta in the spatial direction, and ghost operator in time direction. And in this case, this state is called a co-invariant state, and they are annihilated by the momentum constraint. And Hilbert space is identified by the action of Hamiltonian constraint. So it's a little different. So in this case, you have a equivalence relation up to the Hamiltonian constraint. And you can further consider other co-invariant states, which are annihilated by all ghost operators. In which case, the equivalence relation is given by all the momentum and Hamiltonian constraint. So let me explain more about this, more the intuition about this each state in BRC cohomology. So let's start with the invariant state. So invariant state is the state that satisfies real unification. So this state is basically intuitively is the sum over all possible states at all possible time steps. Whereas the co-invariant state, they are the states at the fixed time slices. But for the middle case, where I just tentatively for time co-invariant state, this is not a proper name, just named randomly. For time co-invariant state is we have the time size is fixed, but we have identification and we sum over all state at the fixed time size over different spatial coordinates. And state with the different time sizes, they are equivalent up to the Hamiltonian constant. The similar thing is true for the full covariant state, where basically the order state is equivalent by up to the Hamiltonian constant. So this is the introduction, and so this is my final talk. So we will consider the matrix. We compute the gravitational passing integral of this cylinder type topology with the initial and final boundary condition, and we will relate it to the inner product in the inner product of the state we talked about in the isolation. So we will relate this the gravitational passing integral with the inner product of invariant state. And we will particularly use the ADM decomposition so that the Hamiltonian momentum constraint easy to see. And furthermore, we will identify what's the resolution identity of the physical unit. And the resulting, the final expression of a passing layer becomes something like this. So this N naught. So yeah, so this N naught is the homogeneous part of the mass, and this is the homogeneous part of the shift, and it's a homogeneous part of the diatom and conjugate moment. So basically, this right-hand side is given by the canonical formalism. But the difference from usual canonical form of the matrix element is that this presence of this integral.
Right.
So
I'm a little bit confused. Like, by passing rule, usually we prepare the boundary condition and compute error factor during that shouldn't be, that should be different moment invariant. Right? The number should be different moment invariant. Then if you say integral product just covariant states, then why did they imagine like it is different moment invariant as covariant states? As itself, it's not. It's like basically a class of states. So the why the passing rule is more invariant equals to the covariant states, because well, like in the say mass field and our paper, they have this rating data, and it's like covariant data, covariant. That's the I'm just trying to make sure like what you mean by the inner product. You include also this rating macros, literally not even the product covariant states, which I don't know if it's equal to or not.
let's see.
Yeah, maybe it will become more clear when you actually show the confidence.
Sure, yeah, that's. Okay, yeah, so this is the first part of my talk, and the second part I will give a model for finite and the model for finite and regression of this Hilbert space, and so one upshot is that this model that the Hilbert space dimension is not necessarily one dimension.
Sorry, what is N?
N is well, roughly correspond to 1 or the okay. So in the case of 2D JT graphics, it's correspond to the S.
So the way, maybe I'm skipping ahead, but the way you obtain that path integral is you start with the JT path integral, then you take some geometry constants and you do AD and you write it in ADN formulas and with some loss function, and then you're basically like choosing some mini superspace.
I'm not using the superspace.
Okay.
General possibility.
It's general?
It's
Okay.
But the restriction is that we restrict the finite and initial information
Okay.
to be constant intervals.
And so that's just basically the JT path integral, but just written in ADN.
Yeah.
Using ADN.
Any other questions? So let me begin by the perturbative Hilbert space. So in this talk, I will focus on the most simple theory, which is JT gravity with the gear-shaped Neumann boundary condition. So we fix the boundary condition to be the boundary metric as well as the boundary between culture. In this case, the theory is just this form without no boundary term, and this theory is basically pure, same as the pure PSAQR theory. And we employ the ideal decomposition with the lapse and the shift function with A square being the density. And yeah, so this lapse and shift parameterize the normal direction to the time space. And for this, the convention is that I periodically identify data. So in rewriting the action by the ADM variables, it's given by its foreign action. Sorry, this is a mistake. I'm considering the Neumann boundary condition. And in terms of the conjugate momentum, this action can be written in the following way, where the carry H and carry B are the Hamiltonian momentum constant. Here, the plus minus sign is correspond to the ADS and BS. So we consider those three things. So before going into the actual gravitational pattern graph, let's begin by the classical solutions. So in the case of ADS, there's only one solution, which is the space-time that's periodically causing a big bang and crunch, and that's continued forever. So that is the solution. And in the case of Rosetta space, it's the classification space-time is not richer. So one example is the big crunch and bounce solution. So you have a big crunch first, and it continues to the big bounce. And yeah, so in this case, you don't have a periodic solution, just causes the bad ones. This space-time is just a portion of the big crunch.
Sorry, let me just locate this event. What is the A prime? It measured from the last slide, so it is
Yeah, so I'm using the A.
It's derivative.
Sorry?
A prime means the derivative of A.
So this, so A prime is the derivative. Is the derivative. Top corresponds to that.
Okay.
It doesn't get notation.
Sorry, how should I be thinking about these solutions? So, yeah, generally these are extendable, right?
Yeah.
If they don't cover the full space time.
Are you this one?
And both.
So I mean this one just continue forever.
What about the singularity? What did we do continue to A equals 0?
So here this is A becomes 0. And continue to the minus value, negative values, and again, go. So for A, is becomes start with negative value, becomes 0, positive value, maximum value, becomes 0.
As a manifold, I don't understand. It's not a manifold, right?
So this is just a notation because the only metric that matters is X squared. So
What I meant is that there's places that look singular.
yeah, sure. Yeah, at this point, this metric becomes.
So normally we don't take that seriously. Like we don't say that it makes sense to say that one thing happens after another. Through the singularity.
Yeah, that's true. Yeah, this is.
Like it's not a single manifold.
Yeah, here just continue the parameter.
Also with both of these, right, they can be embedded into like portions of the thing on the left and the entire thing on the right can be embedded in full, like the thing on the right can be embedded in full decider space, right?
Yeah.
I mean, it's basically just two little points in the diagram. Is there something happening here that's creating singularities on those boundaries, or why are we not fully extending this?
Okay, so this is I'm only considering the space and the period space.
Oh, I'm sorry,
So
yeah.
this is just that.
So these are really singular.
Yeah, this is also. So taking the portion of impact and identify the events.
You stage, that's one, set 0, you didn't hold it to that line, nobody wants to why does it take so little if you don't put it in money?
Yeah, so this is just to get the simple solution.
Okay, so
It's not the general answer.
okay, so it's not case based, so then I can keep right the piece.
So this is just showing the classical solution. So I'm not using. Yeah, so this is just the classical.
So in the decider case, should you also get to regions with close time curves like that? You're only like identifying the worksheet, but there's also like the space like parts of the decider diagram where the identification is like timeline, right?
Yeah, that's.
Don't know whether that's from,
You throw those out for some reason or?
let's see. I'm not sure of that. I didn't have those special signs.
Yeah, no, like it ends in this singularity, but then it closes only.
You have take on the parts, but different.
Yeah.
Uh-huh. Yeah, I'm not sure I need to look up. But at least in this understood, that's usually. Yes. So other solution is like Rosetta bound, so this is just same as global Rosetta. And some non-trivial solution is like NDS, where the diagram becomes at the infinity, the alternating sign is a positive infinity and minus infinity, and so on. So now let's move on to the path integral. So first I introduced this conjugate moment at K with the expense of extra factor to your path integral measure. And original path integral measure for the JD gravity is coming from the ultralocal inner product, which in terms of ADM variable given by this expression, which induces the measure for A squared, which is kind of trivial factor. And in the end, combined with this extra factor, I will arrive at some non-flat measure for your path integral. So extra factor is last times S squared, which is still local, but it's not flat. Okay, we can also obtain this path integral measure using by integrating out some degrees of freedom in DFL, written in terms of variables.
So what did you pull it out from here?
Sorry?
Like, I imagine we start with the PFs,
Yeah.
form the really expressed with these variables and example what you can bring out.
Yeah, so you basically integrate out. So I think you integrate out one of the component in connection omega. And also you integrate out.
Wait, that's because of what gauge fixing?
So you first gauge fix the local lines.
Yeah.
So the change of length first, and you integrate out one component of the connection, and also you integrate out some X field, some of one component of each field. And so another component of the field becomes the P, this P, and another component of the connection becomes K. That's how you proceed, and you arrive at the same, exactly the same theory as the JD graph. In the canonical like format. And this is not really a canonical format yet because we have a non-flat measure.
So yeah, so this is the boundary conditions. So we consider the fixed length and the constant direction curvature. And depending on what sort of set we want to consider, we consider boundary condition for both speeds. For if we want to consider time for invariant state, then we want to consider the boundary condition fixing force moment, force and force momentum, and for the full invariant state, we want to consider force speed to be zero after launch. So that's the two possible boundary conditions for force. But in today's talk, I am not going to consider this first possibility, and I will mainly focus on this second three-point bias. So we fix the boundary condition force to be zero, vanishing at the launch. The similar possibility was considered for mini superspace model in 1988 by Riken. So now we want to do the gauge fixing, and we parameterize isomorphism in terms of the perpendicular direction to the time slice and the parallel direction to the time slice. So I just parameterize these two parameters. Using these parameters, the isomorphism can be written specifically like this. And the gauge fixing condition we will employ is the following. So A prime and K prime being zero, so it's the spatial coordinate we are considering to be the constancy curvature as well as the length density to be constant. So that's one the condition. And second, these two conditions on absolute shift are the condition that basically control so the first condition is control the speed of time slice, and the second condition control the origin, the origin of the spatial coordinate to be only moving and at most moving to be constant. On average. So this gauge fixing condition is general enough. So it is strong enough to kill all the differomorphism local symmetry, but weak enough to accommodate that the gauge transformation is expressed.
Yes, and zero is zero.
Yeah, N0, so N0 is the defined zero.
Yeah, I hope that.
Yeah, if it fix the order lapse shift, it's completely doing too much. And yes, for this fixing, we have a thermal that's written something like this, which is homogeneous. So it is the data independent and at most linear in time. So this model induces translation time and space, but since they act non-trivially on the boundary, they are excluded when we are considering full covariance. So we don't need to consider these elements.
Integral of n including a value. Integral of n including a value.
Interior override, and you mean interior itself?
Oh, the top, you know,
Yeah, we do passenger override.
and both.
Yeah, both. So, yeah, so we, in particular, we are considering the integration rate of laps to be going from -50%.
That warranty only by. Is it 0 to infinity?
Yeah, the infinity is, yes, at least it's very complicated. And imposing the constraint is more non-trivial. Yeah. And we don't have immediate program going choosing to -50%. So yeah, although it's a bit complicated, there could be a problem going into the near to the plus direction. You have a configuration of laps where you go to minus and plus. So that is also can be trivial. So yeah, I guess it's just change concerning the transformation they are given. Positive derivative, the mass. So yeah, so I think we can argue that
Yeah.
but naively that naively, if you have a negative, so if you are considering the laps to be going upward and going backward and going upward again, then you might worry that for the same space-time point, you have a multi-value field that you can imagine. So if you have a time fold, then you have the 3 points where you have as a space-time it is equivalent, but so naively these three points have independent field. So one could worry that there's a multivariate field for space network. But probably this is not a problem with the Gaussian price. Yeah, but this is an interesting point. I have a slide, but it's not going to. Yeah, anyway, so. Yeah, so we can calculate the palette or determinant for this gauge fixing. And in this gauge fixing, it turns out that this the determinant for A and K and laps and shift factorize that one can show. And in the end, we can explicitly compute the determinant, and it becomes this very simple function after some data transformation. But we have to note that this determinant is not applicable to all the possible space-time because each factor can be zero at some space-time, like NDS, precisely at NDS. So for NDS, we have to treat it separately. So the discussion from now on will only apply to the ADS or global DS or quick transplant DS. So that's a limitation in our environment. And yes, so we can integrate out all the Pn and the Phi n in the path integral, which so here the n is just the Fourier mode of the diatom and the momentum. And so I might have shown the Hamiltonian constraint pretty much earlier. So yeah, this is a Hamiltonian constant, and I consider the Fourier series expansion. And path integral of Pn and Phi n act on these constraints and give you the delta function for the spatial part of the Maxwell shift. India. And you have some factor that's precisely cancel with the variable determinant, and you arrive at this result. I think I just this. So anyway, so we arrive at the path integral can be given by this very simple expression. And we know that this can be written as a usual canonical commutation relation on extended matrices. This is not necessarily physical. And the right-hand side can be written in terms of delta language by the foreign expression. So intuitively, the right-hand side sweeps. So this is just a Hamiltonian, the erosion on the Hamiltonian H0, with time being the n naught. And n naught runs from minus infinity to plus infinity. So basically, you start with A prime K prime state, and you sweep you consider time evolution in both in backward and forward in time.
By the way, the integral in between like AK and A prime K prime integral is not the same. In the middle is what I call the Riken map in
Sorry, just to make sure I understood. So, up until now, you were doing a path integral derivation, and you were doing standard LST quantization, and you arrived at the first equation there.
Yeah.
Great. And now you want to, starting from that equation, you want to rewrite it as some canonical quantum gravity expression, where you have your extended or kinematical Hilbert space, and then you go to the physical Hilbert space,
Yeah.
like with this breeding or averaging. And then, so is that something that you're starting from the path integral and just rewriting it like that? Like, are you showing that you can rewrite your path integral result in that way? Or is it, like, I guess what I'm asking is, are you doing two different things and show they coincide, canonical and path integral? Or are you starting from the path integral expression that you already got?
Yeah,
And then just, sorry.
Yeah.
Either way, but in this case, you can also use this path.
Yes, sir. Yeah. You know, I started with the path integral and arrive at this expression, which is manifestly can be written in terms of canonical computation relation. operator with some kind of canonical distribution, and use that operator expression. I can rewrite it in terms of operator like this. So basically, it's a passive integral derivation of this structure.
Does this, it is helpful maybe for solving some, if you instead, suppose you don't know about this final result, you try to, from the start, canonical quantization.
Yeah.
Then, like, that's the fact that you want to know at least the result of the path integral, maybe that help you like how to do the canonical quantization. Because I think in general it's not, at least I don't know that it's always true that the path integral quantization is the same as the canonical quantization. So maybe this can be used to like check, because in the path integral derivation, which has a very clear canonical expression, maybe now we can be, let's say, oh, let's try to do canonical quantization from scratch and see if we also take this.
But then you have to guess it. So there is an argument
Yeah.
against this.
Yeah.
That one argument is yes, yes.
Yeah, you also could you mean that you have assumed that you do group average.
Yeah.
That's a guess, right? Oh,
Yes, yes, yes.
From the canonical side.
Yes,
That's
yes.
a good. But it's a more natural assumption about how to do it. Every gauge.
But even assuming that, right, it's not trivial that the kinematical states that you choose after group averaging will match with the path integral.
Yeah, so that's what I'm deciding from canonical,
Yeah.
whether this is really a product which makes sense. So,
Yes.
always you have to kind of guess what is the
Yeah.
This is very natural in the end.
Yes.
Because the delta function rate is zero.
Yes.
Just zero.
Yeah, but
You can get
for example, the integral has many Milana derivative Milan. And first, if you just consider the canonical compensation of this whole system, then that cannot go through because there's a flat, non-flat measure which doesn't make sense in canonical.
again, I think you can balance it. But where the function of non-zero motion. Yeah, the same.
And so, yeah, so here I integrated out this non-homogeneous part of the diaphragm and the conjugate momentum for A. And only Pn and Phi n appears inside this Hamiltonian momentum constant. And combining the two, that will give you the state function of the non-homogeneous part of the function with the extra factor, which is precisely cancelled with pattern computer.
That's why you don't have properties. Just always zero point zero point eight three.
Yeah, after integrating now, yes.
Is that the two-dimensional ratio or?
Yeah, it's because you need that. It's not just fine errors.
Yes, so these are the example of time. I just quickly say that we can apply this.
You did start a bit late,
Oh,
so I think you still have at least 5 minutes.
Okay, sure.
Yeah.
Okay, yeah. So we can work out this ADS example, and we could take some branch inverse. So in that case, basically, if you in the AK basis, the time evolution by the Hamiltonian constant is just circling around forever in this circle, and we can obtain the inner product of B states being the delta function divided by B. And using that, so basically this B state becomes the basis of your physical Hilbert space. And in the end, you can get the resolution identity of the closed universe Hilbert space, I mean, perturbative Hilbert space by this another space that say similar, have a similar structure, which in the mid-Bankhardt's case is value by beta, which is it's in culture at the similar work. So maybe it's not nice characterization. But anyway, so in this way we can obtain the physical Hilbert space under this resolution. So yeah, so this is the second part of my talk, and this is the model for reproducing this inner product at large n. So the finite element that reproduces this inner product at large n. So we want to consider the d-dimensional Hilbert space, which reproduces this relation at the large n. So the model is the foreign model. So this is a random state model, which is very similar to the PSS1 model. So the ingredient is as follows. So let's consider the random matrix, which is not necessarily unitary. That's mapped from Cn to the Cn. So Cn denote the space of B square and B square. And then the random state we consider is that this B state, which is defined by basically randomly averaging over states, where I is a microscopic state, which is the D dimension. So this is very similar to the PSSI model and also to the non-part of the geodesy length state considered by the Riken and so on. And we can show that this is indeed gives you, and it also contains the one-dimensional microscopic Hilbert space as well, but we can show that this behaves in the expected way that matches with this part of the large n result. So, for example, let's consider the ensemble average of a single matrix element. So you just take the averaging over this random matrix, which gives you the Kronecker delta. So this is so this random state indeed gives you expected behavior. At least that reproduces this relation of the large n. But the behavior starts deviating once you consider the fluctuation of this the matrix element, the product of matrix element. And indeed, if you compute the fluctuation, then it is given by this this Kronecker deltas, which has a following simple Park interpretation. So the leading term is just the original closed universe inner model, giving you the Kronecker delta E prime and times the delta B prime double prime and the B triple prime. But now we have interested in the second term, which connect the B and B triple and the B prime and B and double prime. So what it tells us is that this is can be interpreted by just swapping of the geodesic time size to in between. But now you have extra factor which is divided one by. So when d is equal to 1, this is familiar contribution that lead to the one-dimensional Hilbert space equals. But now we have we can make d to be a general number, and so in this case, what we have modified is that we modify the suppression factor for the gravitational transfer connected different matrix area. So in short, in this way we can consider some non-trivial dimensional microscopic Hilbert space, but with more complicated gravitational transfer. So this suggests that also the kind of null state like constraint on the closed universe Hilbert space. So in this case, two closed universe Hilbert space is not necessarily the tensor product of one closed universe sentence, because if you take the inner product, you have an extra term suppressed by one body. So in particular, when you take d to be 1, the basically antisymmetric part of your tensor of your Hilbert space in the tensor product becomes null state. So it explains that even if you consider the tensor product of closed universes, it's in that case its dimension is state dimension.
Sorry, I'm a little confused here. So what's the parameter like? Isn't it the starting like at the very beginning start with some like random states, and then d is the size of the set here, not the set there. Then if d is literally 1, then you start with 1 state,
Yeah.
right? So what are we confirming here?
So that's the so this is just the example of constraint given here for general dimension. So this is the relation for generally, and when we consider this constraint in one-dimensional case, this relation precisely gives you the null state.
Okay.
So if you just consider from one-dimensional thing, so this result, this part is the kind of trade-offs.
Okay.
It's just going different way. And so basically the main claim is that if you modify your gravitational personnel, that's rating that which rate you feel multiple that connect the different matrix element being suppressed by different manner can give you a non-trivial situation. So this is summary. So what we did is so we consider the gravitational constant zero, and we related it to the inner product in physical Hilbert space, which is the Hilbert space of closed universe, and it's given by the states. And we proposed a finite M model for such state, which can have a non-trivial expansion. And so in that model that you can connect the difference of this element is has a different weighting. So yeah, there are some open questions that what's the role of other homology and what's the calculation for MDS. And it's interesting to include matter and construct some observer using that. And also it's interesting to study the full matrix model for this. Yeah, that's it.
Any more questions? I have one question. So the finite end part of the this picture, yes, exactly. So so the second picture for this 1/d term, right, is red arrows is basically saying that it's the same as this crossing. So I will also think of this as drawing as B, B3, and B prime, B2.
Yeah, it's a different one.
Yeah. And so why is it necessary to do this at finite cutoff? Right? Can I just do this with asymptotic boundary conditions, and then I will have circles of length beta 1, beta 2, beta 3, beta 4, and then I will have, suppose I'm only consider cylinder approximation not to be connected. Then I will have a cylinder beta 1, beta 2, beta 3, beta 4, which is the first term. But then I can also have a cylinder beta 1, beta 3, and beta 2, beta 4.
Yeah, I think we can do that, but the only difference is that in this case, we have a explicit realization of position identity, so it's expression is simple. I think this, yeah, that's the only. And we can see perspective that.
Okay, then I see.
Simple is not.
And are you saying that this 1/d factor, which should be bound to a bigger space, that there's some, does it follow also from this BRST quantization?
Oh, no, it's just follows from modest model.
But if you instead do this BRST, I guess you only got we're only doing cylinders, not two cylinders. Can you compute this inner product using your BRST quantization?
So you mean the topology change?
Yes.
Yeah, topology change, yeah, we are studying that, but
Okay.
we don't know how to do it. Yeah, this one.
Right, so if there are no more questions, yeah.
So in the West Coast model, D is derived from.
Second.
So in the West Coast model, D is derived from the actual model.
So in West Coast model, what they did is they proposed some states similar to this.
Yeah.
And they specifically constructed the gravity law of this, the 2D model with the Endelbrock range,
Yeah.
which precisely correspond to the expectation value of the product of the matrix M.
Right, but you can read the, like for instance, in the calculation of the purity, you can read the replica one Politz action, gives you to the minus S naught. And from there you can derive what D is. But here, I guess the logic is a little different, but can you derive D from a pattern?
Yeah, so I don't have a, I don't have such the Endelbrock model that reproduce this type of.
And you're thinking of this random matrix that goes to some hyperspace Cn to infinity. So actually it's CD, right? Or is it
Yeah, so this is CD.
CD, okay. And so this is, right, this maps some small hyperspace to some large hyperspace, so it's some non-isometric mapping.
Yeah.
So you're thinking of this as mapping like the closed universe hyperspace, CD, to be effective.
Yeah.
Yes. All right, well, let's hand it to the speaker.